Good day everyone, I am Janalyn Bulawit and I am going to discuss about the parallel pipe network that will contain Darcy, Manning, and Hazen Williams formulas and problems. So now let's begin. The Darcy formula or the Darcy-Weisbach equation mainly tend to be referred for this computation and is now accepted as the most accurate pipe friction loss formula. Although it is more difficult to calculate and use than other friction loss formulas, with the introduction of computers, it has become the standard equation for hydraulic engineers. Reynolds number is the basic dimensionless group in viscous flow. Velocity times length scale divided by kinetic viscosity. Relative roughness is related to the height of a typical roughness element to the scale of the flow. So now let's move on to the formula for friction loss. Friction loss formula is HL is equals to F times L over D times V squared over 2G, where F is the friction factor, L is the length of the pipe, D is the inner diameter of the pipe, V is the velocity of the liquid, G is the gravitational constant, and HL is the friction loss. So let's have an example. Find out the friction loss if the inner diameter and length of the pipe are 0.3 meters and 30 meters respectively. Also, the friction factor and velocity of the liquid are 0.4 and 25 meter per second. So we have here the given parameters. Length of the pipe or L is equals to 30 meters. Internal diameter or D is equal to 0.3 meters. Velocity of the liquid or V is equals to 25 meters per second. Friction factor or F is equals to 0.4, whereas G is equals to 9.8 meter per second squared. So now going back to our friction loss formula, which is HL is equals to F times L over D times V squared over 2G. So we just have to substitute all the given. So we have 0.4 for the F times 30 for the L over D 0.3 times V squared, which is 25 squared, over 2, and G, which is 9.8. And then we can come up with the answer that is 1,275.51 meters. So now let's move on to the next formula, which is the Manning's formula. Manning's equation or formula calculates flow parameters for gravity-driven water flow. The formula input values are pipe or channel dimensions, surface roughness, and flow slope. Solving the equation finds the average flow velocity or flow rate. The resulting flow values can then determine the depth of the water or the maximum flow capacity. While computers have made more accurate method practical, Manning's equation is still commonly used due to its simplicity and versatility. So now let's move on to the metric units of the Manning's formula. So to calculate the cross-sectional average velocity, use the following formula. So we have here the formula. V is equals to K over N times RH raised to 2 over 3 times S raised to 1/2, where our V here is the average flow velocity, which is in meter per second. K is the unit conversion factor, which is a 1 for metric units, and it is also dimensionless. Whereas our N here is the Manning roughness coefficient, RH is the hydraulic radius, that is meters in unit, S is the stream slope, equal to channel or pipe slope when depth is constant, which is also dimensionless. So we have to remember also that the RH or the hydraulic radius accounts for the shape of the channel or pipe. Find the hydraulic radius using the following formula. So we have here RH is equals to A over PW, where A is the cross-sectional flow area or meters squared in unit, and PW, which is the wetted perimeter, which is meters in unit. So we already talked about the metric units of Manning's formula. So we have here now the English units of Manning. So the variable of k in the Manning equation is a conversion factor between metric and English units. When using metric, the value of k is equals to 1. When using English units, k is equals to 1.4859. So now, the English form of the Manning equation uses the following variable units. So we have here v, which is the average flow velocity, that is foot per second in unit. K is equals to unit conversion factor, which is 1.4859 for English units, and it is dimensionless. N is equals to Manning roughness coefficient, which is S per feet raised to 1/3. RH is equals to hydraulic radius, that is foot in unit. S is equals to stream slope, which is equal to channel or pipe slope when depth is constant, and it is also dimensionless. A is equals to cross-sectional flow area, that is feet squared in unit. PW is equals to wetted per meter, which is feet in unit. Q is equals to volumetric flow rate, which is the cubic feet per second in units. So we have here an example problem. A water tank on a hill will supply water to a fire engine. The pipe will be made of 4 inches schedule 40 PVC and must flow 0.03 cubic meter per second. What is the minimum required slope for this pipe? So in this example, the value to be determined is S. Since one of the input values is the volumetric flow rate, that version of Manning's equation will be used. Solving for S gives S is equals to n squared times q squared over a squared times k squared times rh raised to 4/3. So once again, k is equals to 1. The Manning roughness coefficient N for PVC is 0.010. The cross-sectional area, or A, of 4 inches schedule 40 PVC is 0.008103 meters squared. The hydraulic radius, or RH, of a circular pipe is the same as its interior radius, which for 4 inches schedule 40 PVC is 0.0508 meters. Solving for the slope S, which is n squared times q squared all over a squared times k squared times rh raised to 4/3, is equals to 0.01 squared, that is the n squared, times 0.03 squared, that is the q squared, all over 0.008103 squared, that is the a squared, times 1 squared, that is the k squared, times 0.0508 raised to 4/3, that is the RH raised to 4/3. And we can come up the answer, which is S is equals to 0.073, and the pipe in question will require a slope of at least 7.3%. So now let's move on to our last formula, which is the Hazen-Williams formula. The Hazen-Williams equation or formula is used to calculate the head loss or pressure loss of water due to its flow through a straight pipe. It does not consider other sources of head loss such as elevation change, direction change, or pipe restrictions. The equation is dependent on the interior pipe diameter, the velocity of the fluid moving through, and the Hazen-Williams coefficient, which describes the roughness of the interior pipe surface and can be found in a lookup table. So using the standard nomenclature and SI units, the Hazen-Williams equation takes the form below. Q is equals to 0.278 times C times D raised to 2.63 times P raised to 0.54, where Q is the fluid flow rate, that is cubic meter per second in units. D is our pipe internal diameter, which is meters in unit. C is the Hazen-Williams coefficient, an empirically derived number that describes the interior pipe surface roughness. And lastly, P is the head loss per length of pipe, which is Pascal per meter in units. This form of the equation solves for the output velocity of the fluid in the pipe given the losses. So the equation above can be rearranged to solve for the head loss over the length of pipe, which is the P is equals to the quantity of Q over 0.278 times C times D raised to 2.63 raised to 1.85, where P is the head loss per 1 meter length of the pipe, which is Pascal per meters. This further implies to P is equals to Q raised to 1.85 all over 0.094 times C raised to 1.85 times D raised to 4.87. To use the equation in this form, the output P gives the pressure loss per length of pipe. You would then need to multiply P by the length of pipe in meters to get the overall head loss for the given pipe section. So as for the head loss form or the US customary units, using standard nomenclature and US customary units, the unit-specific Hazen-Williams equation follows the form below. P is equals to 4.52 times Q raised to 1.85 all over C raised to 1.85 times D raised to 4.87, where our P here is the head loss per 1 foot length of the pipe, which is PSI per foot in units, whereas our Q is the flow rate or the GPM in units. So now let's have here an example. City planning engineers must estimate the maximum head loss of the freshwater delivery pipe that is being installed to a new high-rise. The pipe will tap into the main water line approximately 300 meters from where it enters the building and is made of brass with an internal diameter of 0.28 meters and a flow rate of no more than 6.3 by 10 raised to negative 2 cubic meter per seconds. So use the head loss form of the Hazen-Williams equation to solve for head loss per meter. So we have here the formula. P is equals to the quantity of Q all over 0.278 times C times D raised to 2.63 raised to 1.85. So from the problem statement, the maximum flow rate or Q is 6.3 times 10 raised to negative 5 cubic meter per second, and the pipe diameter or D is 0.228 meters. So the pipe material is given as brass. So from the table of Hazen-Williams coefficients, C is equals to 130. So plugging them into the above equations yields P is equals to 6.3 times 10 raised to negative 2 and raised to 1.85 all over 0.094 times 130 raised to 1.85 times 0.28 raised to 4.87. So we come up the answer with 0.006 all over 1.55, which is P is equals to 3.87 times 10 raised to negative 3. So P is given in pascals per meter of pipe. So the solution above must be multiplied by the length of pipe or L to obtain the overall head loss. So we have here head loss is equals to P times L. So given up all the given to our problem, head loss is equals to 3.87 times 10 raised to negative 3 times 300 meters. So the unit of this is Pascal per meter and times 300 meters. And we can come up the answer. Head loss is equals to 1.16 Pascal. So in this example, the maximum total head loss over the 300 meters length of pipe is 1.16 pascals. And that will be all. Thank you for listening and God bless.